In this video, I want to look informally at what is known in mathematics as an algebraic structure, because what we're going to be doing this semester in our study of modern algebra is we're going to be looking at algebraic structures. Loosely, an algebraic structure is a set with either one or two well-behaved binary operations. Now, exactly what a well-behaved binary operation is going to be left undefined in this particular video, because my point in this video is to look at several familiar examples of algebraic structures so that you get an idea of what we mean by an algebraic structure. So some familiar examples, and let's make my notation just a little bit clearer. So some familiar examples of algebraic structures. First of all, the real numbers under their addition and times. You have known all about the properties of the real numbers for a very long time, and anything that basically has the same properties that the real numbers have under plus and times is known as a field. And you actually probably looked at the formal definition of field in a course like linear algebra course, because fields are important in linear algebra. It turns out that the rational numbers under their plus and times is also a field. But if we look at the integers under its plus and times, this doesn't quite wind up being a field, because fields require non-zero elements to have multiplicative inverses, and the integers don't have inverse of 1/2, rather the multiplicative inverse of 2 is 1/2, and 1/2 is not an integer. And the kind of algebraic structure that the integers form is a commutative ring. Formally, it is a commutative ring with identity. But we also have some other kinds of structures that you may be familiar with from previous mathematics courses. If we let capital M sub little n comma m is going to be equal to the set of n by m matrices, we know how to add matrices of the same size together. And it turns out that this particular set under its addition is something called a commutative group. Now, we can't multiply rectangular matrices of the same size together. In other words, I can't multiply a 2 by 3 matrix by another 2 by 3 matrix. But if I think about square matrices, I know how to add and multiply two square matrices. So the set of square matrices would be m sub n n. This is the set of n by n matrices. And if I take two matrices inside this set, then A plus B and A times B are both defined. And it turns out that this particular set, under its plus and times, winds up being a ring, but it is no longer a commutative ring with identity. So there are lots of these examples that you're already familiar with of sets that have binary operations. There's one more that I want to introduce as reminding you that you may have seen it. If we look at what is often called Zn, and this is the set of integers between 0 and n minus 1, we can define modular arithmetic on this particular set. So we can define a plus b to be equal to c mod n, and a times b is equal to, say, d mod n. And under these kinds of definitions, it turns out that Zn, under its addition and multiplication, is a nice, well-defined algebraic structure, and this also turns out to be a ring. Now, in Math 301, the course that you are enrolled in at Buff State this semester, Math 301 deals with groups, and groups are the simplest of the algebraic structures because a group only has one binary operation. We'll look at the formal definition of a group in a later video.